Okay, so what we're going to look at now is we're going to look at bending. So when we talk with bending, reactions, trusses. To start off with, before we do any of these things, what we have to first look at is we have to look at the beam situation. We have to find the two reactions. Now, typically what we like to do is we like to call this one RA and RB, right? I like to call them RB, sometimes I call it red balloons. Anyway, now intuitively, the simplest case that we have is if we have 100 newtons, right? We're using 100 newtons rather than 100. We typically use kilonewtons for these sorts of situations, but let's say we've got 100 newtons. It's only a 10 kilo weight. If we have that in a beam that's 20 meters long, we have something that's 20 meters long, how much do you think each side is going to have to hold it?
50.
50. Right, that just makes sense, right? Because it's symmetrical, we can assume that our reactions, I'm going to use a blackboard for that, but I'm not going to rub that up because I'm lazy. 50 and 50. Right. Said I wouldn't rub it out, and I did because... Anyway, okay. What about in this situation here, where we have 100, we'll stick with beams for the moment. We have 100 units, still a 40 meter, it's okay, now a 40 meter beam, it's a very long beam. We have a 40 meter beam, and what we have is we want to divide it, we want to divide this load now. What would we predict would be the likely case? What would we predict to be the likely distribution?
33 and 66.
So you think, okay, so about a third, so if we're going to say 1/3, imagine that these are two people holding this, right? So we've got Adam and Bob, right? And they're holding this beam. Who do you think is going to have to hold more? Bob. Okay, so you think Bob's going to hold more. He's taking more weight. Okay, so Adam's going to be holding more weight. Now, how much more weight do you think he's going to be holding? I heard a third, or like
3/4.
3/4. 3/4. There we go. That's better. 3/4. So because there's 40, he's 1/4 of the distance. He's going to be taking 3/4 of load. Now I'll say that this is not the way we normally teach this topic. I just want you to know that this happens to be true. And it's intuitive. I'm trying to use what makes sense to you in your head. Now what we can do is we can prove that. We can prove that using a formula. Now I'm going to sit, because I'm going to tell you at the bottom of the screen. What the formula looks like is it looks like this. First of all, we have to say we're going clockwise or anti-clockwise. I'm going to say we're going clockwise. I will always say that we're going clockwise. Then we have this symbol sigma. Sigma means, capital sigma in this case means the sum of whatever we're doing. Well, that was really quite off center. Okay, then we're going to have the capital letter M. So they're moment forces. We've done some of the forces before, now we're doing some of moment forces. Whenever we do this, we have to measure from one location. So we can measure from a reference point of A, or we can measure from the reference point B. Which one do we want to use? I don't care. A. So we're going to measure everything from the position A. And we're going to say the sum of the moments are equal to 0. Because we're in equilibrium, these beams, we're always assuming it's in equilibrium. And the reason we assume that is because if it's not in equilibrium, it's broken. Yeah, as a civil engineer, if something's moving, it's probably broken, right? So if it's not in equilibrium, it's broken. So we're going to say it has to be in equilibrium, which means the sum of all the forces and the sum of all the moments have to be equal to 0. Okay, so we're just going to write that formula now. We know that whatever we do, it's going to equal 0. So we're going to say 0 equals... Now, what is the formula for moment?
Force times perpendicular.
Moment equals force times perpendicular distance. Oh, that's not what I meant to do. Wait, I did want to do that. Okay, force times perpendicular distance. Okay, so if we're in our formula, if we go from left to right, what's our first force? Okay, well, it's going to be reaction A, but we could put it in here for the moment just to see if it works, right? Our first force is 75, and how far away is it from point A?
0.
It's 0 meters away, yeah? It's 0 meters away. Now, is it going clockwise or anti-clockwise? Well, it's going straight through, so it's not turning it at all. So at that point, we can ignore that. The next force we have is 100 newtons, yeah? The next force is 100 newtons. I always write the distances in brackets. That's what I do. Now, so I always write the minus sign, and then I figure out if it's clockwise or anti-clockwise afterwards. So minus 100, and then let's have a look at it. if I put a pin on A and I press down on the beam here, will it go clockwise or anti-clockwise? Which way is it going? Relative to point A, that force is going to turn this beam in a clockwise direction. We've said that clockwise is positive, so we're going to make this positive. So I'm going to turn that minus into plus. Now, what was its distance? 10 meters. 10 meters. Now, in a situation like this, because the distances are relative, we could just convert that. But we'll leave it there because I don't want to confuse people. But we could just knock off the zero, and sometimes that can be useful. We'll see later why that can be useful, but for the moment we're going to live with it. The next force, that we only have 3 forces in this diagram. 1, 2, 3. The next force is what?
25.
25. Okay, so what we're going to have is we're going to say minus 25. Now, is it going clockwise or anti-clockwise? Relative. If I put my axle for my wheel on A and I press up, it's going anti-clockwise. So we're going to leave that as a minus sign. How far away is it from A?
40 meters.
40 meters. It is 10 plus 30, which is equal to 40 meters. Okay, so let's have a look. Let's see if our statement is true. So we're going to have 0 equals 0 plus 1,000 minus, can someone do that maths for me? I think that seems right.
0.
Is that true? Did it work?
Yeah.
Hey, our prediction worked. Right, so that's great. That's our first. Now, what have we found there? Well, we've proven that this one is right, but we haven't. Well, we'll leave that for the moment. We'll leave that for the moment. We will actually use these unknown reactions in a second. Okay, but just to start off with it. Now, let's take this situation. What we're going to do here is we've got, this is our load case. What is above my hand is what we're going to look at. This what we're going to call equation C. So above equation C, how many forces do we have now? 2. Okay, I hear 2. Does anyone have a different answer? 4. 4 is the answer I was hoping for. But thank you for looks. You know, you guys, they all built on your answer. Okay. So what we have here on the left-hand side, we're going to name this. We're going to name this point A. We'll name this point B. And what are we going to call this force? RA or RA. And this one we're going to call RB. Why are we calling it RA and RB?
Reactionary reaction.
That's exactly right. The reaction at point A, which we often just call reaction A, and the reaction at point B, which we call RB. Okay. Now, if we look at this, if we break that down into its forces, we can have a look and say, well, what's our prediction? If we were at 50 and it's 10 meters and 20 meters, what would we predict that our answer will be? Okay, it's 50 and it's 1/3 of the way here and it's 2/3 of the way to that side. Yeah? This load is 1/3, right? It's 50. What do we think we're going to do? I'll write it down for you to help you out.
16.6.
Does that seem right?
Yes.
Yeah? Okay, so we could actually rub that out now and say, so 50 times 2/3 is 33 1/3. And this will be 16.7. You happy with that? So because Adam is standing 1/3 of the distance to the force, he's taking 2/3 of the weight. Yeah? If you've ever carried something with someone else and you know that, hey, I'm holding it closer to the weight, you'll know that you're carrying more of that weight. If you've ever helped someone move, for instance, you might have noticed this. Right? So he's holding closer to the center of the mass, he's going to be carrying more weight. Okay, the next guy, right, he's taking 21. Now this time, for the 21 force, Bob is closer to the weight. So how much is Bob going to get? How much do you think Bob's going to get? He's going to get 2/3 that weight, yeah? So what's 21 times 2/3? Equals 14. And what's this one? 7. Right? So 21 times 1/3 equals 7. Now, what we can do is we can add those up. What's 33 1/3 plus 7?
40.3.
Sorry, 40.3. Yeah. And what's this side? 30.7? Yeah? Now, let's test that out, right? I'm going to clear off this part of the board. I'm going to clear off this part because this is not how people normally do this equation, right? This is not how we do it in real life. I'm just trying to show you how intuitively it works. If we just take what we understand to be about holding things and lifting things,
Well,
right?
Put one after all.
I haven't done it for a week.
What is our prediction? Our prediction is that we're going to end up with RA equaling 40.3, and our prediction is we're going to end up with RB equaling 30.7. That's our prediction. Now, at this point, all we're working is with vertical forces, right? Yeah, that's all we're working with is vertical forces. Let me see if our prediction makes sense. Well, let's start off with, so the sum of the forces vertically equals 0, right? Because we're thinking there's an equilibrium of forces. If it's not an equilibrium, it's broken. Now, in my prediction, I've got 4 forces here, right? I've got, to start with here, I've got RA, and RA is going 40 up. 40.3 up. Yeah, we're happy with that. Then I've got 50 down. So I'm trying to draw this roughly to scale. 50 down. Then I'm going to go down another 21. Yeah? And then I'm going to go up. How much do I need to go up for that to equal? Well, let's have a look. Does 30.7 work? Do we get 71 on this side and 71 on that side?
Yeah.
Yeah? Okay, so boom. Hey, our test worked. Yeah? The forces balanced in the vertical direction. We have equilibrium in the vertical forces. Okay. Now what I'm going to show you now is the way that we actually do this equation, right? Because in the HSC you don't want to be drawing out the diagram 4 times, right? I'm trying to show you that it could work. And look, I have actually seen engineering textbooks, the tables and things to help people do these things, where I have actually seen textbooks that use this method, but I've never known anyone who uses this method either in the HSC or in engineering practice. Instead, what everyone does is they use this formula that we looked at just a second ago, where we say the sum of the moments equal 0. Now, when we do that, we always want to assign a direction so people know what we're looking at. Now, the HSC, on occasion, has gone from clockwise, sometimes it goes anti-clockwise as positive, right? At uni, I would say more than half of my teachers used anti-clockwise as the direction. But I am now going to use clockwise as positive always. The reason I do that is if I'm consistent in one direction, we're consistent forever, and then you guys, I'm not confusing you. When you get to uni, you'll be so comfortable with this, you won't be confused when you have teachers starting to do it backwards. So I'm going to say clockwise. It's the same way that we could use down as positive. I'm always going to use clockwise as positive. Now when we do this, the reason why we use this is because at the moment we have 2 unknowns. Yeah, we have 2 unknowns. And we can't solve equations with 2 unknowns unless we do something to eliminate one of those unknowns. At the moment we don't know what RA is and we don't know what RB is. But the magic of moments is that we can use the perpendicular distance to make this equal 0, right? The amazing thing about moments, so I'm going to write down the formula for moments is moments equals force times distance, that's the perpendicular distance. Yeah, that's what, okay. Now, if I take moments from this point here, all of the moments will equal 0. If I take moments from point here, all the moments will equal 0. If I take moments from there, doesn't matter if I make it from any of these locations. If I go from C, if I go point C, point D, or point E, It doesn't matter. All the moments will equal 0. But why do we want to take moments from point A? Because if we take moments from point A, it will help us find point B. Yeah? Why will it do that? Because we will be setting the perpendicular distance as 0, and we'll now have an equation with only one unknown. I'll show you. I'll do an example. Okay. So what we're going to say is 0, because we know the whole thing has to equal 0, equals, I'm just going to go forces from left to right. 1, 2, 3, 4 forces. Our first force is RA. Now I'm going to write a minus here because I don't know if RA is going to be positive or negative yet. RA, I don't know if it's clockwise or anti-clockwise. Now, measured from point A, which direction is RA going clockwise or anti-clockwise?
Anti-clockwise.
Well, it's actually going straight in. It's not pushing anti-clockwise, it's not putting it's neither. Why? Why is it neither? Because it's times 0, and 0 isn't positive or negative. Yeah? So RA is just going to be multiplied by 0. We can ignore that. You don't have to write that, and a lot of textbooks will not write that part, because they're like, we just ignore it. It's now multiplied by 0. That's the whole point of using moments, is we can ignore one of these forces, and we ignore the tricky one. In this case, RA is the tricky one. Ra is the tricky one. Next, we're going to move on to 50. Now I want to write the minus sign because I don't know if it's clockwise or anti-clockwise yet. Okay, so I'm going to push down on the beam, and I'm put my finger on the axle at A, and then I'm pushing down at 50, and I'm going right? Clockwise. So I'm going to turn that into a plus. Now, how far away is it from A? 10. So times 10. Okay, next we get to this next force, 21. I'm pushing down. Is it a plus or minus? Plus, right? Because it's going clockwise. Okay, how far away is it? 20. Now, I like to write 10 plus 10, just so that way, a lot of people write 10. A lot of people they see a 10 there and they write 10. They don't remember that we're measuring from A, distance from point A. Now, lastly, we're going to do our reaction B, right? So I'm going to write minus RB. Is RB, now we're making an assumption here, right? We're assuming up. And if we assume that it's up, that means, is it going to go up?
Yeah.
Which way?
Anti-clockwise.
Anti-clockwise. So we're going to leave that as minus. How far away is that?
30.
No, I'll write 10 plus 10 plus 10. Which is 30. Now, if we assume that that's clockwise, if we assume that it's up, we're going to assume that it's anti-clockwise, therefore negative. Yeah? Now, what we're going to see is at the end, if our answer is positive, our assumption was correct. If our answer is negative, our assumption was wrong, because sometimes we assume that the arrow is going up, but in some tricky situations, when we have cantilevers, it might actually be going down. Yeah, when we have sort of like trusses or gangtrees or something like that, we might actually have the force going down. So we've made an assumption, and I've written in blue. You don't need to write this, but I've written, assume the force is going up, therefore anti-clockwise, therefore negative. Right? And at the end, if our answer is positive, we're going to say our assumption was okay, therefore the direction was the direction we said it was going to be. Okay. Now let's rewrite that equation, right? Well, let's simplify that equation. We're going to say 0 equals 0, which we don't even need to write, plus 50 times, so it's going to be 500, plus 420, minus 30 RB. Is everyone happy with that? Okay, now I'm going to make a simplification here, and I'm going to say, I'm going to do this once and once only, and after this point I'm going to assume that you understand this concept. In order to move this 30, I need to go plus 30 RB here, and plus 30 RB there. Now that's a year 7 concept. I remember I used to sit next to this guy called Dean, and I remember spending quite a lot of time trying to help him to understand this concept. But he just struggled with that the whole time, right? It was not something he was ever great at. So what that does is that eliminates the 30 on this side and it puts it here. Now I don't think of it that way. I just think of it as the 30 goes to that side. Hopefully you guys are all like, why is he spending so much time talking about year 7 maths? Hopefully. Right. So what we've got is 30 RB equals 920. Yeah, is that right? Everyone's happy with my maths?
Yeah.
Okay, now if I went to the shops, again, this is the only time I'll do this. After this, I'm going to assume that you know it. If I went to the shop and I bought 30 red balloons for 920 bucks, how much was each balloon?
920 divided by 30.
Yeah? Give me a rough idea. How much is each balloon?
30 point.
About 30 bucks. Now, I want you to do that every single time, right? That is an incredibly important thing because so often people will make some mistake and they'll say, does that number even seem sensible? And in engineering, you don't want to be the guy who, when you go and take your work to your boss to verify, he says, what were you thinking when you wrote that down on a piece of paper? Because I tell you, I've never had that happen to me, but I've seen it done to my peers, and I tell you, it's a terrifying conversation that you do not want to be having. So, RB equals, I'll get the exact values.
30.7.
30, yeah, 0.67, and that's obviously 6666 repeated, I'm just going with that to 7. Now, the value is in kilonewtons. We didn't convert back to newtons at any point. Now, we have to, it's a vector. Vectors have direction. Which direction? Okay, so I've got someone pointing up. Why is it up? How do we know it's up?
Because it's a reaction force.
Because it's positive. And we made an assumption. We said that if it's up, or we've assumed it's up, so if our answer is positive, we say positive, therefore our assumption was okay, therefore it's up. Right? Now you don't need to write that, all you need to do is you just need to include that arrow, and you will lose marks for not including that arrow. Okay. We've just done our first question. Right. We've got it. Now once we've found RB, we could do that whole thing again to find RA. Yeah? Are we happy to do that? Okay, so first of all, we're happy with this one. This one's here. We're done. We're going to tick. Now, we could take moments from B and see if it works. Why not? We'll just do this one a little bit faster. Okay.
Is there a faster way than doing that? So
We don't need to do moments from B again. What we can do is we can just add up the vertical forces. Yeah, we did what we did at the start. We can just do the sum of the vertical forces, and that saves us one equation. But I would say to you, when you've finished the exam, you're sitting there doing nothing, go back and do what we're doing now. Take moments from the other side, and that's what serves as a very effective check. If it works from both directions, you're happy. Okay, so measuring from B. So we've got 0 equals RB times 0, which is 0, so we don't even need to write that. So I'm actually not going to write that this time. I'm going to say I could write RB times 0, which equals 0. You know what, I'll do it just this once, right? Okay, then working back, we've got minus 21 times 10. Is it clockwise or anti-clockwise? Well, if we put our pin on B and we turn it, we go do-do, do-do. Anti-clockwise. So we're going to leave that as a minus sign. Okay, the next one we're going to have 50. Minus 50. And its distance was 2 times 10. Okay, again we're going pushing down, down, down. Yeah. What's that? Which direction is this? Anti-clockwise. Okay, lastly we have RA. Okay, so RA is going pushing up. Relative to B, it's going up, up, clockwise. So we're going to turn that into a positive. How far away is it? 3 times 10 away. I'm going to change markers just to the full. These markers are harder. Okay, so I'm going to simplify that. I've got 0 equals minus 2100. Oh, sorry, just to go back, I'm going to state my assumption here. I'm going to say here, assume up, therefore assuming clockwise positive. Okay, minus 2010, and this is 50 times 20 is 1,000, right? Plus 30 RA. So I'm going to move that just over this side. So I'm going to say minus 30 RA equals minus 1210. So RA equals minus 1210 divided by minus 30 equals 40.3. Now, it's kilonewtons, positive, and you don't have to write the stuff in blue, but what I'm saying is it's positive, therefore the assumption was correct, right? So therefore it was up. Yeah? Okay, that we don't have to do that, but if you have time at the end of the exam, this is a really useful way to spend your time because it checks. The third part that we can do, which I've already done, is sum of the forces vertically. Sigma forces vertically equals 0. And what have we got? We've got 40 minus 50 minus 21 plus 30.7.
You don't need to write that.
Does that work?
Yeah.
We're happy. Yeah, our check worked. Now you can do any two of those three. Yeah, you can do any two of those three. Most people like to do this one instead of moments from B because it's a little bit faster. Okay. Yeah.
So, what does this mean?
Okay. What we're going to do now, and this is going to be the end of what we're doing now. If you go to the book, and I'm going to put it on the screen for you.
This, sir,
Yeah.
did you get this?
Not the time. Okay. On this page, example 1.1, on page 14, page 14, example 1.1 of the book. Guys, looks a lot like this question we've got here. The only difference is that what we have now is instead of having 21 newtons, what we have is 30 newtons at 45 degrees. Now, why would we get this situation? Well, we'd get this situation if we had, we could have machine parts like cranes, for instance, that have to deal with or some sort of a rope system that might be pulling loads on. Or probably more realistically in this situation, something that's 30 meters long, it might be a bridge, and if you have a vehicle stopping. And when a vehicle stops, it exerts a force into the bridge at an angle. Yeah? So that's probably the load case that we're looking at here, is we're looking at a vehicle stopping on a bridge. Now those vehicles weigh, just for like context to give you an idea, so they weigh that many newtons, which means that they're about 3 tons. What we're looking at here is a car that's 3 tons and a truck that's 5 tons, and this truck is stopping and it's exerting a force into the bridge at 45 degrees. Okay. Now, in this situation, it's very similar. If we follow through the book, well, what we need to do is we need to find the forces. We're going to worry first about the forces vertically, but what we need to worry about as well is we need to worry about who is going to take the horizontal forces. Yeah, so when we look at our reactions, only one of these can take reactions. Who of these can take a horizontal reaction?
B. That's RA.
It's RA. RA. Because Ricky the roller, right? Ricky the roller can't take horizontal. She just won't do it. Right? She just refuses. Whereas Penny the pin, well, she'll now we don't know which way she'll go, but she'll take the reaction. Now, if we have RA, what I'm going to write that now is I'm going to write that as RAV. What do you think the V stands for?
Vertical.
Yeah. vertical component of the reaction at point A. And here we're going to write RA, anyone want to take a guess? H. Okay. So what we're going to do now is we're going to do the same thing. What we're going to start off with, because we have now 3 unknowns. Yeah, we have 3 unknowns. We now have RAH unknown, RAV unknown. But how can we eliminate those unknowns? These pesky, annoying unknowns. How can we eliminate them? Take moments about A. Because if we take moments about A, all of these get multiplied by 0 and they drop out of our equation. It's pretty amazing. So, we're going to set, which direction should we set as positive? Clockwise or anti-clockwise? Clockwise, that's what we want to do? Okay, no problem. Now, we're using, there's 3 proofs that we use in this subject. We use some of the forces horizontally are equal, some of the forces vertically are equal, and some of the moments are equal. Which equation are we going to use to start off with? Well, we can't do vertical because we've got 3 unknowns, or 2 unknowns in that situation. Here we have an unknown, we can't figure that one out. So what we're going to do is we're going to use the sum of the moments. Now, which location do we want to take our moments from? We could go from here, or here, or here, or here. But which one is the most useful place to take our moments from? From A. If we do that, we can ignore all of this business. And we're going to say that because it's in equilibrium, it's always in equilibrium. If it's not in equilibrium, it's broken. Because it's in equilibrium, the sum of all those forces have to be equal to 0. So, we're going to write 0 equals, and we just go in our direction. Now, I promised I wouldn't write these anymore, so I'm just not even going to write the 0. If you want, I'll write 0 just to acknowledge that there was a force there. Yeah, I'm just going to write 0. If you want to write out the whole thing, if you want to write RA times 0 is 0, that's fine. Your textbook won't. That's why I just want to point that out. Your textbook won't even write that in there. Yeah?
50 kilonewtons is that 50,000 newtons.
50,000 newtons. It's 5 tons. Yeah? 5 tons on Earth gravity. Hey, just one sec.